Hi everyone, my name is Eno. I'm a principal engineer in AWS. I'm happy to be here with Rajiv, who is a principal developer advocate, also in AWS. Today we'll talk about how AWS makes data streaming easy for you. So first, we'll talk and give an overview of what data streaming is. In the focus of the talk is going to be two exciting open source projects, Apache Kafka and Apache Flink. They are key components of a modern streaming pipeline. We'll talk briefly about what they are, what they can do for you, and how we in AWS make it easy to run them. And of course, we'll have a demo towards the end. So what exactly is streaming data all about, and why do we care? So in this graph here on the x-axis, we have time. We have time going from real time to months. On the y-axis is the value of data to decision making for a business or a customer like yourself. On the right-hand side of the graph, we see historical data. Typically, this data is collected over a period of months and is processed in a database or warehouse periodically, once a day or multiple times a day. On the left-hand side, we're seeing data that's often time critical when it comes to making decisions around it. This data is often actionable, and the actions you can take on it can be predictive and preventative. It's this left side of the graph that this webcast is mostly about. So this is what we call streaming data. And the importance of this is that oftentimes a subset of the data, in fact, this streaming data, often loses value quickly over time. So if you don't react to it quickly, often some of the value there can be gone forever. So it's this left-hand side of the graph that we'll focus on in the rest of the webinar. Now, where is this data coming from? Where does this streaming data come from? Well, one can argue that most of the data actually starts as streaming data first, and then eventually it becomes historical data. So this data can come from mobile applications and what they collect on the phone as your phone reacts to some of the applications. It can be the traditional clickstream on the web, where the clicks and the advertisements are both captured and later analyzed. It could be metering records. This is important, especially if you're billing for resources that you're consuming, such as CPU, storage, or the network. It could also be data that's coming from IoT sensors. And these sensors nowadays are pervasive. They can be in your car. They can be part of the smart buildings infrastructure in your city. And these sensors capture things like temperature, velocity, and they constantly generate data. Now, what do we actually do with this data once we collect it from all of these sources? Well, even here, we have a range of options. First of all, in this, what I'm calling millisecond range, oftentimes we find applications such as microservices that are using this streaming data to communicate amongst themselves. Oftentimes, in the past, they have used things like RPCs, but nowadays, we find that most of them are actually using streaming data for multiple reasons. One of them is because of the reliability it provides and also the ability to rewind back in time as the applications are trying new things. In the middle here, we have the second time range. Here, oftentimes, we're aggregating a lot of this streaming data per second, and we use this for things like log ingestion, IoT device maintenance, and also to capture multiple changes in your database. These are often called change data capture, or CDC kind of workloads. And then on the right-hand side, we have minutes. Here, presumably, we've processed some of the data. We have kept only the most important bits of it. And then periodically, every few minutes, we'd like to stream this data, perhaps transform it along the way by dropping some columns or adding some more data or filtering some of the data out. And then ultimately, we store it into data lakes or data warehouses. So why capture and process the data in real time? Well, through that, businesses typically can more easily react to customers in real time, react to threats and environmental changes, and make timely decisions. which ultimately mean that these businesses can innovate down the road faster. So what are the building blocks around real-time analytics? Well, there are a couple of building blocks here. In this picture, we see around 6 of them. And we can start with the simpler one, which is really the source. The source of the data, as we discussed earlier, can be a device or an application that produces real-time data, often at high velocity. This source, multiple such sources, are then taken into the second stage of the pipeline, the stream ingestion stage. Many of them are aggregated and put together into what can be considered as a stream. Now, a stream is really an abstraction. Oftentimes, it means unbounded records, an unbounded number of records. They keep coming, they never end, that belong to a category. Okay, so for example, velocity measurements from cars, okay, or temperature measurements, they belong to the same category. The third stage is quite interesting, is the stream storage stage. So in this particular stage, this is really motivated by the customers, and we have this interesting differentiator here to traditional queues. In traditional queuing systems, you get a message, and that message is removed from the queue permanently once the customer has received it. In stream processing, we often find that customers like to actually store these data streams, for example, the car velocities or the temperature measurements, for the longer term. So where do they store them? Well, they store them in a storage system that's appropriate for this kind of data that's unbounded in nature. So data is stored there, sometimes temporarily, sometimes for the long term. And then the applications, so that's the next block, stream processing. These stream processing applications that analyze the data, they might compute various aggregations, they might join it with other data. Because the data is stored for the longer term in stream storage, the stream processing applications have the ability to try different algorithms with the data. They can do A/B testing and move forwards and backwards in time and process the data as they see fit, multiple times if necessary. And then finally, once the stream processing application has finished its processing, it takes the results. Oftentimes, it stores the results in a destination such as a data lake or a database. The stream processing component here can do things, can do processing like stateless processing or more stateful processing. But the bottom line is that the results are stored in a destination where oftentimes they are aggregated with other data you might have around in your ecosystem. For example, the historical data that we showed in the graph, for what we're calling all-time, real-time, and historical time processing. So when we take these building blocks, which are conceptual, and then we materialize them into what AWS has to offer, in this slide here, for both the storage and the stream processing, I've replaced those blocks with 2 concrete building blocks that we offer. The first one in the stream storage space is Amazon MSK, which is a service around Apache Kafka. We're going to spend some time to talk about it in the next few slides. And the next one is Amazon KDA for Java, Kinesis Data Analytics for Java. And this is a service built around Apache Flink, which is another popular open source system library that's built for stream processing. Now, before I go into each of them in detail, let's zoom out a little bit. So I just showed one box for stream processing, for example, but there's many more. In this webinar, we're going to zoom in Kinesis Data Analytics with Apache Flink, but it's important to notice that on AWS, there are many other third-party services that run that can provide good stream processing as well. Components such as Apache Kafka Streams, Apache Spark, with various third-party vendors backing them over there. So the picture when it comes to stream processing is very nuanced. There's lots of options out there. The principles behind it we'll show in this webinar through one concrete offering that we have, Amazon Kinesis Data Analytics for Java. So zooming back in there, what is Flink and why did we choose Apache Flink? Well, it turns out that Apache Flink allows certain things that customers really care about. It allows for stateful processing. Stateful processing usually means sophisticated and useful processing such as aggregation, joins, and these are all done at large scale in a distributed system. The second thing it has is it has the ability to provide exactly one semantics and processing. And this is exactly one support is especially important for critical applications in fraud detection or in banks or in the financial industry. Applications that really care that your data is processed correctly from start until end. So what are the current trends that we're seeing in stream processing? Well, let me recap a few of them here. The first one I alluded to, I mentioned the data streams are already replacing message queues. Queues were simple. You put a message there, a record there, you consumed it, and that was it. We find that customers nowadays would like to do many more complex, much more complex processing with their data. And for that, they have moved from queues to data streams that allow them to store and replace these records over time, multiple times. The second one is the data streams are replacing Hadoop workflows in many scenarios. As companies, as customers are moving to more real-time analytics to gain more insights over their data, naturally some of their batch processing jobs are moving more and becoming stream processing jobs. The third one, we talked a bit about microservices. That's one way that applications, a modern way that applications are built nowadays. And the data streams are really becoming the spinal cord for how these microservices are built. All the communication among them happens through data streams. And finally, we're also noticing that typical analytics that usually used to be in the realm of relational databases, things like query processing and queries that typically looked relational in nature, they're happening more and more on data streams as well. So those are the trends that we're noticing out there. Now let's go and zoom in into one of the components of the pipeline, into Apache Kafka. So Apache Kafka is one of the components in the stream storage layer that we talked about in the pipeline. It started at LinkedIn a couple of years ago, and it's one of the most active Apache open source projects out there. It's very popular with developers. It did start as a simple pub subsystem many years ago, but it has evolved over the years to do a lot more than that. So in particular, it's used nowadays for real-time analytics, messaging, transaction and event sourcing for databases, and also streaming ETL. Let's look a little bit at Apache Kafka from a high-level point of view. The customer typically only notices the libraries that Kafka has, the producer library and the consumer library. In the middle, there is a cluster, the Kafka cluster itself. The cluster is made of brokers. The brokers are responsible for storing the data as well as for replicating it to ensure high durability and availability for the system. Apache Zookeeper is used for coordination of the brokers and of the producers and consumers with the rest of the cluster and ensures that the entire cluster is alive and well. Let's look a little bit deeper now into the producers and consumers. Starting with the producers, the first thing we notice is this notion of a topic. Here we have a topic with 3 partitions, shown like cylinders here. Now, a topic is really an abstraction. It's an abstraction over unbounded data. You can think of it as a topic being a particular category where messages belong to. The topic itself is an abstraction. It's made of partitions as the unit of scale. So a large topic with a lot of data often also has multiple partitions. That is one of the ways that producers and consumers scale in a Kafka cluster. Now, each of these partitions is append only. which means that data from producers doesn't override the previous data there, but it's often written at the head of the log. So this abstraction of a topic and partitions really give you this abstraction or this illusion of a never-ending distributed log inside your system. Now, you can choose, the customer can choose to retain the data in this log for the short term or also for the long term. In fact, there are some common use cases where the data is retained in Kafka indefinitely. What about the consumer? So the producers produce the data inside these topics, and now we have the consumers reading that data from the topics. Now, the first thing to notice is that these partitions, you can think of them as persistent queues, which means that they decouple the speed with which producers send the data to the system with the speed or the ability of the consumers to actually read the data from the system. So here is a consumer group. You can think of a consumer group as an application with 3 consumers inside it. Each of these consumers is independently consuming from each of the 3 partitions respectively. The last consumer, the one in the bottom, is slightly behind. It's only been able to consume 2 records, and more records have been produced in that particular partition. So it might be a slow consumer, but the bottom line is that it eventually catches up, and the buffering inside the system, this persistent buffering, these partitions, really act as a speed matching buffering between the producers and the consumers. The neat thing about Kafka is that it's built with high availability in mind as part of the protocol itself. So here's an example where the 3rd consumer fails. What happens is that Kafka itself starts what's known as a rebalancing protocol, and it spreads the load with no downtime on the other available 2 consumers inside the system. This ability to spread the data and rebalance it gives Kafka the ability to be highly available with respect to consumers. Now, if this was a transient failure and the 3rd consumer comes back up again, the same rebalancing protocol happens, and eventually the load is balanced again the way it was before. Now, if you zoom out from this picture, oftentimes you have many consumer groups, which means many applications in your system, independently consuming from each of these partitions. In fact, in this particular case, they're consuming all the data from this topic completely independently from each other because they are very different applications. So this is a typical picture of Kafka in what we call a pub/sub mode, which is really how Apache Kafka started with. Now, Apache Kafka is a library ultimately, and there are many challenges operating it in production, especially at large scale. First of all, Kafka tends to be difficult to set up. We saw in the picture there are lots of brokers there. There are zookeeper nodes as well. Many of the brokers have hundreds of configuration parameters, and it's just difficult to wrap your mind around how to set that set of parameters correctly for your application. It's also difficult to achieve high availability for Kafka. Oftentimes, naturally, we need to patch servers, patch some of the brokers whenever security updates are released, make updates to Kafka or Zookeeper itself. We might want to add storage to the system as well. And it's just hard to do that, or rather, the library, the Apache Kafka library, doesn't necessarily dictate on how this high availability should be achieved. So it really leaves it up to the customer to ensure that high level of availability. It's also expensive to maintain. Over time, as the workload changes, the customer might find, for example, that they'd like to add more storage to Kafka, or they'd like to add more brokers or more partitions. And this all becomes expensive and burdensome and requires a certain level of expertise that is difficult to find. So to address the challenge, we have released, and we have had this under production for over a year now, Amazon MSK, which is a fully managed and highly available and secure service for Apache Kafka. What it does for you is that it allows you to focus on application development and less on infrastructure and Kafka management. So this formula here is just one way to write that. The effort to maintain your application should really be a function of your own application rather than maintaining the infrastructure around Kafka. So MSK drives best practices through design, through good defaults, and through automation of most of the operations in the cluster. Now, one of the benefits of running Amazon MSK is the many customers with their various workloads that come to our system from which we learn and share some of this information to improve the open source Apache Kafka in the long term. So getting started with Amazon MSK is quite easy. It's fully compatible with the open source Apache Kafka. We have a management console. We also have an API for provisioning. Clusters can be set up automatically in minutes, and also there is the ability to tear them down also in minutes. The service itself provisions Apache Kafka brokers, Zookeeper, the right instances, and also storage space. It also allows you to create and use different configurations from the default and also change them over the runtime of the cluster. Now, one thing I wanted to describe before moving on to the next section, which is Kafka, the way we run it in Amazon MSK is secure by default. Not only do we run between the clients and the brokers the accepted security protocols, but we also run MSK, we also run Apache Kafka as part of a services VPC. So here we have a customer's VPC accessing the cluster, who is running in AWS's VPC. The customer does not see any brokers or any Zookeeper nodes in their console. The customer only sees what's called ENIs or elastic network interfaces. And the service itself takes care of all the configuration of the brokers and the Zookeepers and storage behind the scenes. So Amazon MSK is secure by default. And the VPC connectivity, this slide just shows one way towards that. Now I'll hand off to my colleague Rajiv, who is going to segue into Kinesis data analytics for Java applications and talk about the second building block here, which is stream processing on top of streaming data.
Hello, everybody. My name is Rajiv Chakrabarty. As Eno had mentioned before, I'm a principal developer advocate with the Kinesis team, and I'm happy to be here with you today. So let's get started. So Kinesis Data Analytics is a fully managed AWS service that enables you to use an Apache Flink application to process streaming data and to produce outputs. Your application then writes that output to a configured destination. So how do you build an application using Apache Flink, and how do you deploy it to Kinesis Data Analytics? It's actually a very simple three-step process. Basically, you build your Apache Flink application locally in an IDE of your choice, like IntelliJ IDEA, which can also allow you to run and debug your application in an Apache Flink engine running within the IDE, and then make your application code available to the Kinesis Data Analytics service by uploading it to an Amazon S3 bucket. The Amazon KDA for Java service would then run your application in a service-managed Apache Flink cluster. For users, it is a serverless architecture. Applications are built using the Flink programming model, and the application code is made available as a fat jar with required dependencies baked in. Let's talk a little bit about Apache Flink. It has a simple programming model with simple and flexible APIs. It provides a distributed engine, which can be run over a cluster of machines that provides parallelism and in-memory computation that allows for low latency and high throughput. You can build stateful applications, and Apache Flink provides exactly once guarantees and high availability and recoverability. Applications can be written in a variety of APIs that range in expressiveness and conciseness. Flink provides 3 layered APIs. Each API offers a different trade-off between conciseness and expressiveness and targets different use cases. At the bottom, process functions are the most expressive function interfaces that Flink offers. They process individual events from 1 or 2 input streams or grouped window events and provide fine-grained control over time and state. You can therefore implement complex per event business logic as required for many stateful event-driven applications. Next up, the data stream API provides the primitives for many common stream processing operations, such as windowing, inline record transformations, and enrichment and decoration by querying an external data store. The data stream API is available for Java and Scala and has functions such as map, reduce, and aggregate, and others. At the top, there are 2 relational APIs, the Table API and SQL API. Both of these APIs are unified APIs for batch and stream processing. The Table API and the SQL API leverage Apache Calcite for parsing, validation, and query optimization. They can also be seamlessly integrated with the data stream and dataset APIs and support user-defined functions. These APIs are very helpful when you're dealing with data analytics, ETL applications, and other data pipelining applications. In addition, Apache Flink has several libraries for common data processing use cases, including complex event processing and Jelly, which is a graph processing library. The basic building blocks of Flink programs are streams and transformations. A stream, as Eno explained earlier, is a never-ending flow of events. And a transformation is any operation that takes one or more streams as an input, does some kind of an operation or aggregation on it, and produces one or more output streams as an output. Essentially, an Apache Flink program consists of the following steps. You first have to go ahead and obtain an execution environment. Next, you create a source of data and then load the data. After that, you can specify one or more transformation operations strung together on this data. And then you specify where to put or sync the results of your computations. And finally, you go ahead and trigger the program execution. Flink is a lazily evaluated system, and therefore execution is explicitly triggered by an execute call on the execution environment. And until that happens, Flink does not actually execute the program, but it actually records each one of those operations and builds a plan. Flink provides some mechanisms for fault tolerance, and they include checkpoints and save points. Checkpoints make state in Flink fault tolerant by allowing state and the corresponding stream positions to be recovered, thereby giving the application the same semantics as a failure-free execution. Every function and operator in Flink can be stateful. In order to make state fault tolerant, Flink then needs to checkpoint the state. Flink's checkpointing mechanisms are inspired by the standard Chandy-Lamport algorithm and is tailored to Flink's execution model. By default, Flink's checkpoint is not meant to persist and are only used to resume a job from failures unless you explicitly specify that they be retained. Checkpoints are meant to be lightweight and facilitate fast recovery, and is possible to do asynchronously and incrementally, depending on the state backends used. However, checkpoints cannot be used to recover from code changes, parallelism changes, updating the Flink version, etc., while save points can. Checkpoints are also created, owned, and released by Flink without user interaction. In contrast, save points are created, owned, and deleted by the user and can be used similar to backups in relational databases for recovery, and they do survive job termination. This diagram illustrates a job graph for a Flink job and shows a Flink job reading from a source, in this case, Amazon MSK, applying transformations, and then syncing to multiple destinations. Apache Flink supports many operators common for stream processing frameworks, and you can see some of which are mentioned on this slide. This is by no means a comprehensive list of everything. If you want to look at it, you can go ahead and go to Flink's website. In order to be able to connect to different sources and destinations, Apache Flink includes a number of predefined data sources that include reading from files, directories, and sockets. In addition, there are a number of other connectors which are bundled together with Apache Flink that enable interfacing with other third-party systems. Some examples include Apache Kafka, Amazon Kinesis streams, which can be used for both source and sync, and so can Kafka. Apache Cassandra, which could be a sync. Elasticsearch, which could be a sync. Apache NiFi, Twitter, Google PubSub. So these are some of the other ones. Additional streaming connectors for Flink are being released through Apache Bahir, and they include, among others, Apache ActiveMQ, Apache Flume, and Redis. The Apache Kafka connector has both source and sync in a Flink Kafka consumer and a Flink Kafka producer. The universal Kafka connector that does not track a specific Kafka major version, but rather tracks the latest version of Kafka at the time of the Flink release, has been available since Flink version 1.7.0. If you use the Kafka broker version 1.0.0 or newer, you should use this Kafka connector. If you use an older version of Kafka, then you need to use the connector corresponding to the broker version. And to use the connector in your code, you have to import the connector into a Maven project as described in this slide. Okay, now that we have some basics of Apache Flink, let's go ahead and build a clickstream use case. So what we'll do is we will go ahead and talk about a clickstream use case where we'll analyze some user activity. In this case, I have a producer, which is a mock producer of clickstream data for an e-commerce site. The scenario is that a user logs into the site, lands on the home page, browses the product catalog, lands on individual product pages, and then either adds the product to the cart or not, and continues to do that until the user either creates an order and does order checkout or abandons the session. The producer generates these events in a user session in sequence, so it maintains state and order, but runs multiple threads to simulate multiple users hitting the site at once. Our goal is to process the events and get some insights, namely the number of user sessions over time, the average number of events per user session over time, the average number of events per user session resulting in a buy over time, and the average percentage of user sessions resulting in a buy over time. These are very common analytics for a clickstream use case. Here is an example of the events generated by the clickstream producer for a single user. So conceptually, the producer is simulating the click events happening in a web application. These events are being sent to a topic in the Amazon Managed Streaming for Kafka cluster. Those events are then being processed by an Apache Flink application running on Amazon Kinesis Data Analytics for Java. This app then applies a number of transformations and generates a number of analytics in the incoming event stream and sends them to other topics in the same Amazon MSK cluster, while also sending them to an Amazon Elasticsearch cluster that is visualized using Kibana. So here is the demo environment. So this environment, which was created with a CloudFormation template, it created a new VPC with 3 private subnets, 1 public subnet, and other necessary VPC plumbing. So it created a new MSK cluster as well, with 3 broker nodes in 3 private subnets. It also created a public EC2 instance, which has a running Confluent schema registry, and also is the instance where I'd run the Kafka producer. This producer can then utilize multiple threads, as I mentioned before, to parallelize event generation. And the number of threads can be specified by using parameters. Also, the time to run, so how long the producer is going to run, can be provided via parameters. I will keep it running for 30 minutes. One important thing to note here is the VPC connectivity for the KDA for Java app. This is provided by the ENIs, Elastic Network Interfaces, dropped by the service in the private subnets as shown. Since the producer sends Avro encoded messages to Amazon MSK, the Apache Flink KDA app requires access to the schema registry running on the EC2 instance, which is also provided by those ENIs. And as Amazon MSK also drops the ENIs in those subnets, as explained by Eno before, the Apache Flink KDA application is also able to connect, read, as well as sync data into the Amazon MSK cluster through those ENIs. So in this case, the producer sends these events to a topic, which we call example topic in the MSK cluster. So let's go ahead and switch over to the demo. And the first thing I'll do there is go ahead and run the producer. So here I have the command that's going to run a jar file, which is my Kafka producer. And as you can see, it is now starting to send events over to an Amazon MSK cluster to a topic called example topic. And it's going to keep doing this for about 30 minutes because that's what's provided in the parameter to this jar file. Okay. Now that events are being sent to MSK, we need to consume and process the events. To do that, we have an Apache Flink application. Let me do a quick walkthrough of the code. The first step is to set up the stream execution environment. Next, I set the time characteristic to event time. This is done so the timestamp in the actual events will be used by Flink for window evaluation instead of the clock time of the machines in the Flink cluster. This is called processing time. Next, I enable checkpointing. The default for KDA applications is 60,000 milliseconds or 1 minute. Here I'm setting it to 20 seconds in the code, which will override the KDA application setting. Next, I'll load the Flink application properties. This is loading the environment variables provided to the Flink KDA application when the application is created. And it is loaded into the application at runtime so that the values can be used by the program. I'll show those when we go over to the KDA application. Next, I set up the source, which is the Amazon MSK Apache Kafka cluster. And I specify the properties, which includes the bootstrap servers, which is essentially pointing to the Amazon MSK cluster where I send events to. I also specify a group ID, which can be used to look at the consumer lag. In addition, I also provide the topic name and the Confluent Avro deserialization schema, which uses the Confluent schema registry to decode the average Avro messages sent by the producer. There's one other thing I do, and that is to set the app to read the Kafka topic from the beginning of the retention period by this. And I also assign timestamps and watermarks for event time. This is needed for Windows to progress when using event time. Next, I get into the actual calculations and aggregations. Here, I sessionize incoming messages so I can do aggregations within a user session. To do that, I use a predefined Apache Flink window type called session window. In this, I specify a gap, which is if two consecutive messages for a single user are separated by more than this gap, then Flink would create two sessions. Otherwise, the messages would be considered to be part of the same session. To do that, I first key by user ID. Then I do aggregates, which includes the number of clicks in the session, products visited, number of clicks to a buy, and the window begin and end times. I also have two other aggregations. This time, I'm using a tumbling window to calculate the number of user sessions in the last 10 seconds and the percentage that ended in a buy, and the number of visits per department in the last 10 seconds. It denotes the popularity of certain products in terms of user views. Finally, I create syncs. I create syncs for both Amazon MSK and Amazon Elasticsearch, and sync or send those events to both Amazon MSK and Elasticsearch. This is to illustrate that other downstream systems can consume these messages from the Amazon MSK Apache Kafka cluster independently, while also utilizing a Kibana dashboard on top of Amazon Elasticsearch to visualize the analytics in real time. Now let's hop on over to the KDA for Java application. This application was created by the CloudFormation template. If I scroll down to the VPC section, you can see that there is no VPC information provided. So at this point, the KDA for Java application will not be able to connect to the MSK cluster or the schema registry, which is running on an EC2 instance. So we're going to provide that information now. So we click on Configure, expand the VPC connectivity section, and choose VPC configuration based on Amazon MSK cluster. And then choose the MSK cluster our producer is sending messages to. This will automatically populate the VPC and subnet information for the KDA app based on the Amazon MSK cluster information. Then we'll go ahead and remove the existing security group and choose a security group created by the CloudFormation template expressly for the KDA application, which has access to the Amazon MSK security group. There are also a couple of other changes that we need to make. First, we go over to the monitoring section and enable CloudWatch logging. Next, we scroll up to the properties section. And we see that we have some properties already defined. This was again done by the CloudFormation template. These properties are available to the KDA app at runtime through application properties in the code. These properties will then used by the app to connect to the Amazon MSK cluster, find the schema registry to decode the Avro encoded messages, identify the topic to read, also the Amazon Elasticsearch clusters to send analytic events to, and the list of topics in the Amazon MSK cluster to send the analytics outputs to. However, we need to update the default values of Bootstrap servers and Zookeeper connect string to reflect the correct ones because it is currently using the default value of localhost. Let's hop over to the Amazon MSK console to grab those values and update them. Now let's go ahead and click on update. Okay. Now we can go ahead and run this application. It can take several minutes to start running. Okay, now the application is running. So we can go ahead and refresh the page to see the DAG, the directed acyclic graph. So you can see the DAG over here, which basically describes the plan for Flink to execute the application. Also, let's scroll down and click on monitoring. Here we need to make sure that the first graph, which talks about downtime, is 0. As you can see, it is 0 over here. If it is non-zero, then there is a problem with the app, and we would need to investigate it. So at this point, the application is processing those events, creating the analytics as explained in the code walkthrough, and is sending it over to both the Amazon MSK cluster and to Amazon Elasticsearch. So let's hop on over to Kibana. So here, the CloudFormation template has already created the Elasticsearch indices, but we would need to create index patterns, which would then be used to create visualizations. So let's go ahead and create an index pattern. And for time filter, we will select window end time. Let's create another index pattern. And same for time filter, we would use window end time. And create one third one. So now that we've created the index patterns, we can start visualizing them. So go ahead and click on visualize, create a visualization. We'll select a line graph. And first we'll do create a visualization on top of the departments count. On the x-axis, we're going to choose average as an aggregation over the field department count. On the x-axis, we will select date histogram over window end time. But in addition to that, we'll add a sub bucket. We'll do split series, and we'll create an aggregation. In this case, we'll aggregate on top of terms, and the field we'll select would be department name keyword. At this point, we'll go ahead and run it. As you can see, it is showing a bunch of departments over time, and the number of user sessions that have been visiting those departments or products over time. So here you can go ahead and change the time period. It says last 15 minutes. If you want to go ahead and change it, you can change it over here. We'll go ahead and save this visualization, and we'll call it department counts over time. Confirm it, save it. Then we'll go ahead and create another visualization. Again, select line, and this time select the index pattern user session counts. Again, expand the y-axis, choose average, select a field, and here we'll do person sessions with by, because that's an important metric for clickstream analysis. And on the x-axis, we will select a date histogram. And go ahead and hit select. So as you can see, it tells us the average percentage of sessions which is actually end up in a buy over time. And it's somewhere hovering between 45, so let's say between 40 and 45%. So for about 45%, or between 40 and 45% of sessions or user sessions are actually ending up in buying something from that e-commerce site. So let's go ahead and save this. Okay, now let's go ahead and create a dashboard. So now we've created a dashboard with these two particular visualizations, and obviously you can create more visualizations based on the incoming data. And we can go ahead and refresh it, and it will keep adding additional data as the data appears. So basically what you're seeing here is the ability to visualize it on Kibana in real time as events are being generated and sent to the Amazon MSK cluster. So that wraps up the demo. Thank you for your time. Hope you enjoyed this session. We would appreciate your feedback. And now we have time for some Q&A.